Hello everyone, welcome to the Biochemia web channel. I'm here with the topic titled Solutions and Biophysical Phenomena. Let's start. The contents of this topic are solutions, which we will talk about solubility, dispersion, hydration, and concentration units, such as percentage, mass, molarity, and normality, PPM, PPB, and dilution. But the second major content is biophysical phenomena, which I will explain: osmosis and osmotic pressure, dialysis, diffusion, surface tension, and absorption. And the first title is solutions. After a brief introduction, we will continue on solubility. Most matter with which organisms come into contact, however, is a mixture composed of two or more pure substances. The air we breathe is composed of nitrogen and oxygen, together with small amounts of argon, water vapor, carbon dioxide, and other gases. Seawater, such as, is composed largely of sodium chloride and water, and the mixture may be heterogeneous or homogeneous. Systems with the same properties of matter, such as temperature, density, and refractive index, are called phases. If a system consists of a single phase, it is called a homogeneous system. If it contains more than one phase, it is called a heterogeneous system. A homogeneous mixture is a uniform composition throughout a sample. A heterogeneous mixture does not have a uniform composition throughout the sample. Heterogeneous systems are mixtures of substances in which phase boundaries appear. The upper surface of a phase is called the phase boundary. A suspension is cloudy and heterogeneous. Homogeneous mixtures are either solutions or colloids, but here we have a question mark. Yes, a solution, also we call it a true solution, is a homogeneous mixture containing small particles, and the liquid solutions are transparent. A colloid is a homogeneous, but here we have a question mark, because a colloid contains larger particles and often with an opaque appearance. And yes, at the macroscopic level, the colloids are homogeneous, but at the microscopic level, the colloid is heterogeneous, because the colloid carries larger particles which they do not spread homogeneously at every point of the liquid. Thus, actually, in nature, the colloids are heterogeneous. And here you see a classification of matter. Anything with mass and volume is a matter. If carry one component a pure substance, more than one component is mixture. A pure substance can be an element which cannot be broken down into simple substances, or a compound composed of two or more elements. A mixture can be heterogeneous, non-uniform composition, and a homogeneous uniform composition. And a solution, here which carries small particles, are the homogeneous, and the colloids, large particles, homogeneous. But again, don't forget the question mark. In nature, in microscopic level, colloids are heterogeneous, not homogeneous. So be careful. And the new subtitle, solubility. Solubility is the amount of solute that dissolves in a given amount of solvent, usually reported in grams of solute per 100 milliliter of solution. In other words, gram per 100 milliliter. A solution that has less than the maximum number of grams of solute is said to be unsaturated. A solution that has the maximum number of grams of solid that can dissolve is said to be saturated. If we added more solid to a saturated solution, additional solid would remain undissolved in the flask. And also this is called supersaturation, or this is called actually precipitation. And we have another state which is called the supersaturation. And the supersaturation is a state of a solution that contains more of the dissolved material than could be dissolved by the solvent under normal circumstances. Thus, according to the solubility of the solid, we have unsaturated solutions, or we can prepare unsaturated solutions. We can prepare saturated solutions and supersaturated solutions. In this illustration, as you see, comparing the state of unsaturation, saturation, supersaturation, and precipitation. In an unsaturated solution, this is a solution or is a chemical solution in which the solute concentration is lower than its equilibrium solubility. A saturated solution is a chemical solution containing the maximum concentration of a solute dissolved in the solvent. Supersaturated solution. A supersaturated solution is a solution with more dissolved solute than the solvent would normally dissolve in its current conditions. Supersaturation is achieved by dissolving a solute in one set of conditions, then transferring it to other conditions without triggering any release of the solute. And supersaturated solutions are extremely unstable, and if you continue to add more solute, it will be a precipitate. According to the amount of solute, we can prepare either a dilute solution or a concentrated solution. And the dilute solution contains a small amount of solute per liter of solution. A concentrated or a dense solution contains a large amount of solute per liter of solution. And here the picture is depicting a concentrated solution and the dilute solution. And as you see, in a concentrated solution, which the blue particles are the solid particles and the lavender one is the solvent particles. And lots of solute in a small amount of solvent will give a concentrated solution. And here, a small amount of solute in a large amount of solvent will give us a dilute solution. Most ionic and polar covalent compounds are soluble in water, a polar solvent, and the best polar solvent. Nonpolar compounds dissolve in nonpolar solvents. So as you see, there are two classes of solvents, polar solvents and nonpolar solvents. And hydrophobic substances such as hydrocarbons dissolve in nonpolar solvents. And carbon tetrachloride or benzol is an example of nonpolar solvents. And since such substances dissolve very well in fats and oils, they are also called lipophilic substances. Water-soluble compounds are ionic or are small polar molecules that can form hydrogen bonds with the water solvent. For example, solid sodium chloride is held together by very strong electrostatic interactions of oppositely charged ions. When mixed with water, the sodium cation and chloride anions are separated and surrounded by polar water molecules. Here you see a picture showing the solution of sodium chloride in water. The crystalline sodium chloride here, composed of sodium cation and chlorine ion, and they are formed with the ionic bonding and the water molecules. And don't forget, the water has a dipole character. And when the ionic sodium chloride dissolves in water, the crystalline sodium and chlorine interactions are replaced by new interactions of sodium and chlorine anions, sodium cation and the chlorine ions. And these new interactions occur with these ions and between these ions and water. And each ion is surrounded by a loose shell of water molecules arranged so that the oppositely charged species are close together, as seen here, the chlorine with the hydrogen side of the water, which is partially positive, and the sodium interact with the oxygen side of the water molecule, partial negative charge. Ion-dipole interactions between sodium cation and chlorine anion and water provide the energy needed to separate the ions from the crystal lattice. The water molecules form a loose solvent shell around each ion. The process of surrounding the particles of a solid with solvent molecules is called solvation. Small neutral molecules that can hydrogen bond with water are also soluble. Thus, ethanol in alcoholic beverages dissolves in water because a hydrogen bond forms between the hydroxyl group in ethanol and the hydroxyl group in water. When solvation releases more energy than that required to separate particles, the overall process is exothermic, thus heat is released. When the separation of particles requires more energy than is released during solvation, the process is endothermic, thus heat is absorbed. Nonpolar compounds are soluble in nonpolar solvents. As a result, octane, a component of gasoline, dissolves in the nonpolar solvent carbon tetrachloride. Animal fat and vegetable oils, which are composed largely of nonpolar carbon-carbon and carbon-hydrogen bonds, are also soluble in carbon tetrachloride, but are insoluble in a polar solvent like water. These solubility properties explain why oil and water do not mix. And after definition of solubility, it's time to talk about dispersion systems or disperse systems. A dispersion is a system in which distributed particles of one material are dispersed in a continuous phase of another material. And the two phases may be in the same or different states of matter. If one component is present in greater quantities than the other, this component is called the dispersion medium or the continuous phase. The one with fewer components is called the dispersed phase or discontinuous phase. And there may be more than one dispersed phase in a dispersion medium. And there are three types of dispersion systems, which there are solutions. And due to sometimes solutions and the dispersion system using interchangeably, here I especially wrote the three solutions. But don't forget, in real, the solutions are type of dispersion systems. In true solutions, or just solutions, dispersed phase particles less than 1 nanometer in diameter. And the second type is colloids, which the dispersed phase particles are between 1 to 100 nanometer in diameter. And the third one is suspension. Dispersed phase particles are larger than 100 nanometer in diameter. And so this means, and this information tells us dispersion systems are differentiated from each other by the size of the particles, but not only the size of particles. There are also other features such as visibility, movement of particles, osmotic pressure, Tyndall's effect or phenomena, and also the passage of particles through a semi-permeable membrane. And here in my opinion, a good table which will help you during study the differences between true solutions, colloids, and suspension, as well as their features. So, in true solutions, the first feature that we need to compare is the particle size, and I told in true solution smaller than 1 nanometer, between 1 to 100 nanometer in colloids, and larger than 100 nanometer in suspensions. True solutions are homogeneous mixture, and remember about the colloids, we say they appear homogeneous, but in real they are heterogeneous mixture, and suspensions are also heterogeneous mixtures. True solutions behave like a third unit other than soluble and solvent. And a good example is sodium chloride. Sodium chloride is a solid material, water is a liquid material, and if you prepare a solution containing sodium chloride in a volume of water, it is called desaltic water, and it has different features, such as the conductivity feature, which the crystalline sodium chloride does not conduct electric, but the solution in water conduct electric. What about the viscosity, which is tendency to flow? True solutions love viscosity, colloids high, suspensions even very high. True solutions possess osmotic pressure because these solutions contain osmotically active particles in a higher content, and colloids lower, and suspension does not show osmotic pressure. True solutions, when the light passes, the light is eliminated. In colloid, Tyndall effect occurs. When the light passes, it gets foggy, and also it happens in suspensions, or may happen in suspensions. Particles cannot be seen even with the most powerful optical and H-ray systems in true solutions, but in colloids we can observe them using an electron microscope. In suspension, even with the eye, we can observe the particles. In true solutions, particles make molecular movements. In colloids, particles make Brownian motion, and suspension slow Brownian motion is seen. For true solutions, filtering the particles through the filter paper is not possible, even in dialysis. In colloids, the particles are separated by filtration through the filter paper, and also separated by dialysis. In suspension, the particles are separated by filtration through filter paper or by dialysis. So in true solutions, we cannot filter the particles, but in colloid suspension, we can. And also, I want to tell something more about the colloids. And the colloids, I said, they are heterogeneous mixtures in which particles of an insoluble substance are suspended along another substance. And the colloidal solution, sometimes we call colloidal solution instead of colloids, often described as a colloidal suspension too, because it's a mixture in which substances are usually suspended in a liquid. A colloid is a very small material, usually diffused from another substance. And colloidal solutions are usually composed of the following components. Actually, it happens in other ones: a dispersed phase, a discontinuous phase, also we call it the internal phase. And it consists of very discrete particles, often larger than ordinary molecules, and yet these small solid particles are usually dispersed in the solvent. And the dispersion medium in colloids, which one's the dispersed phase also. The medium which include dispersed phase, it consists of continuously interlocked molecules. Another figure representing the difference between solution, colloids, and the suspension, and here you see a solution, homogeneous mixture, as you see, clear like the salt water in this aquarium, and here in this photo the particle diagram in this photo particle diagram shows 90 small red spheres dispersed equally at each part in each space of the liquid. And here milk, a colloid, the particles are much larger but remain dispersed and not settle. And here the corresponding particles diagram shows about 25 medium-sized reservoirs, and look at the distribution. And here is an example of suspension mud, which is a heterogeneous mixture. Suspended particles that looks cloudy and particles can settle. And this is a illustration showing the particle diagram below 10 fairly large reservoirs. And this figure represents the Tyndall effect, when the light source is directed into solution. The light beam is not visible, but in colloid suspension is visible. Here the examples: water, milk, and fluoride. Water. And the Tyndall effect is the scattering of light by particles in a very fine suspension and colloid. Particles in a colloid are large enough to scatter light, and the phenomenon called the Tyndall effect. It can make colloidal mixtures, such as beams from a searchlight, appear cloudy or opaque. Shining a flashlight beam into a glass of milk is an excellent demonstration of the Tyndall effect, and you can try it at home. And you may want to use skim milk or dilute the milk with a little water, so you can see the effect of the colloid particles on the light beam very well. And another examples of Tyndall effect in everyday life, such as the visible beam of headlights in fog in a car, is caused by the Tyndall effect. Water droplets scatter light, making headlight beams visible. And also Tyndall effect is also used in commercial and laboratory settings to determine the particle size of aerosols. Clouds are also colloidal mixtures. They are made up of water droplets that are much larger than molecules but too small to collapse. And I'm sure that you observed before the beam of sunlight going down to the ground, and you can easily observe them. And another picture, the pulse of the searchlight. Here you see beams, searchlight beams become visible when light is scattered by colloidal particles in the air. Homogeneous mixtures of two or more components are called solutions. So the only true solutions are homogeneous mixtures. In any phase of matter can form a solution. When two substances form a solution, the substance present in the lesser amount is called the solute, and the substance present in the larger amount is the solvent. So actually in here, if we're talking about the solutions, a type of dispersion system, the dispersion medium of a true solution is called, dispersion medium is called solvent. The dispersed phase or the discontinuous phase of a true solution is called solute. And don't forget, there can be more than one solute in a solvent, or there can be more than one solute in a true solution. And if we prepare solutions using water, we call them aqueous solutions. And here are some types of solutions, such as air, two or more gases. Air is a solution of gases, mainly nitrogen and oxygen. Here, and this is a saline solution, which contains sodium chloride, dissolves in liquid water. And here you see the dental filling. Dental filling contains mercury, a liquid dissolved in solid silver. An aqueous solution that contains ions conducts electricity. whereas one that contains only neutron molecules does not. A substance that conducts an electric current in water is called an electrolyte, and the sodium chloride solution is a good example of an electrolyte. A substance that does not conduct an electric current in water is called a non-electrolyte, and hydrogen peroxide can be a good example for a non-electrolyte solution. And aqueous solutions prepared with ionic substances or the substances which can ionize in their dissolved state are good can be good electrolytes. And examples are acids, bases, and salts. And here you see an illustration depicting the features of non-electrolyte, as you see here, and electrolyte solutions. And there are two types of electrolyte solutions that after a short time I will explain. But before, let's talk about the non-electrolyte solution. As you see here, when the substance is dissolved in molecular state or dissolved in non-ionized forms, so there is no charged particles in the solution, thus no electric conduction to the lump, and lump does not switch on. And ethanol, distilled water, hydrogen peroxide are good examples. And in here, the substances are completely dissolved in ionized state, in full state, and electric conductance occurred, and the light is on here. And so this is an example of sodium chloride solution, and we call them strong electrolytes if the substance completely ionized. But in this example here, still it's an electrolyte solution because the light is on, but the intensity of the light here is lesser than the strong electrolyte. And as you see here, look at the particles, they are partially ionized. And so we call them weak electrolytes. And an example is acetic acid, or the solutions of organic acids in general, they are weak electrolytes. For a substance to conduct electric current, it must have free electrons. This event is present in metals too, but in a different manner. Anion and cation must be present in this structure. Compounds do not conduct electricity in solid state. Think about the sodium chloride as a solid sodium chloride. It does not conduct electric current. But in liquid form and in solutions, ionic compounds, or ionic solutions conduct electric current. As the number of ions in a solution increases, or as the temperature increases, the conductivity of the solution increases. The electrical conductivity of metals is due to the flow of electrons. It's different, as I said. This is called the translational motion. The phenomenon is physical. But in solution, it is chemical conductivity. Solutions of substances that dissolve in water as molecules, as I said, network, do not conduct electric current. In liquid solutions whose solute is not volatile, the boiling point of the solution is higher than the boiling point of pure solvent. Freezing point of the solution is lower than the freezing point of pure solvent. The vapor pressure of the solution is lower than the vapor pressure of the pure solvent. So, as the amount of solute or the concentration increases in liquid solutions whose solute is non-volatile, boiling point rises, freezing point decreases, and vapor pressure decreases. And the new title, hydration. In the dissolution of a solute, the crystalline building blocks are separated from each other and transported into the solvent. Meanwhile, these building blocks are surrounded by solvent molecules. In other words, they are solvatized. So actually, this is a kind of solvation, which the solvent is water. Thus, as a private or as a narrow range definition, we call it hydration, or we want to refer in the solvation process, the water is the solvent, and we call it hydration. So if water is used as a solvent, this event is called hydration. And here you see a good animation showing the hydration process, which the solvent water dissolve ionic compounds, or ionic compounds dissolve in water. So the water, don't forget, this has a dipole character. So the type of the solvent is a polar solvent. And when the ionic compounds interact with the water, the attraction between ions and the dipole or character of water happens. But as you see, the particles, cations and anions are dissolving, are separating and dispersing through the water. I think it's enough. Let's continue. Yeah. In other words, ionic compounds dissolve very well in polar liquids because polar solvent molecules attract the opposite charge ions in the compound with ion-dipole attraction process and surround the ion with solvent molecules. And such ions are called solvatized ions. In the dissolution of a substance in water, the mobile cations and anions are formed, and both types of ions show an inverse arrangement against water molecules. When a naked cation is surrounded by a solvent molecule, a remarkable amount of energy is released, and this energy is called solvatation energy. The smaller an ion is and the larger its charge, the more strongly it is solvated. A large solvent gap leads to a larger diameter of the solvent gap and reduced movement of hydrated particles. The passage of particles through membranes with small pores is also hindered. This phenomenon is important in the transport of substances across cell membranes. Since a solution has a lower vapor pressure than a solvent, it boils at high temperature. The boiling point rise of a solvent is directly proportional to the number of particles dissolved in the solvent. And the same is true for the freezing point drop. A solution freezes at lower temperatures than a pure solvent. And now it's time for the concentration units. Concentration can be measured in several different ways using mass, volume, or mole. There are different units of concentration, and one of the most common is percentage concentration. That is the number of grams or milliliters of solid per 100 milliliter. So we mean the milliliter of a solid in 100 milliliter or grams of a solid in 100 milliliter. Such as if you want to prepare a 10% of glucose solution, this means we will weigh 10 grams of glucose, and by adding it to an aqueous solution, actually put it in water or mixing with water and then fill up to 100 milliliter, we will obtain 10% glucose solution. And be very careful here, the volume given is the solution volume, not the volume of solvent. So this is the total the volume of solution. Be careful. In addition to percentage, units of measurement such as molarity and normality are also used. If we look briefly, what are the common concentration units we use? The percentage, which there are three type of percent concentration: weight, volume, weight. And then the molarity, normality, and PPM and PPB. Let's start with the percent concentration. And percent concentration is a measure of how much solute is dissolved in every 100 units of solution. And a type of percent concentration is weight, volume, percentage, number of grams of solute dissolved in 100 milliliter of solution. And I gave examples just in 2 minutes ago. For example, if I want to prepare 5% of sodium chloride, the thing is I will weigh 5 grams and then getting a volumetric flux such as having 100 milliliter. I will put the 5 grams of sodium chloride into volumetric flux and then pour water to fill up 100 milliliter, and we will obtain 5% of sodium chloride solution. So a solution containing 5 grams of sodium chloride in 100 milliliter of solution. Be careful. The 100 here is the total volume of solution. So the volume percentage means the ratio of the volume of the solute to the total volume of the solution multiplied by 100. And actually it's a kind of dilution, which we have an equation: concentration, initial concentration, and volume equals the last concentration and volume. So, or in general, if I want to prepare 10% of solution according to the volume percentage, I will take 10 milliliters of a matter and fill up to 100 milliliters to prepare the solution. Thus, I will add 90 milliliters of solvent. So I said it's a dilution because dilution is a process by adding more solvent will decrease the concentration. So we don't add any more solute, we just increase the volume of or the amount of solvent to decrease the concentration. And there is an equilibrium between the initial and the last phase, which is given by this equation, and we will use it every time. And here you see the volumetric flux, the glassware, and also it's a kind of equipment because we use them to measure the volume of liquids or the volume of solutions in the lab. And they are the critical components of every lab. We need them, we use them every time. And as you see here, there are 4 different sizes of volumetric flux, sizes in volume: 20 here, 10, 25, and 50. So depend on our requirement, we can get different sizes, or we need different sizes in the lab because sometimes we want to prepare just 10 milliliter for an experiment, or sometimes we want to prepare maybe 500 milliliter for the experiments. Before discussing the molarity or the molar concentration and normality or equivalent concentration, we should discuss about the mass. A chemical formula provides information about which elements the compound contains, their ratios, and quantities. And remember the atomic mass unit and the molecular weight from the previous topic. If you don't, please check the previous topic, which is matter and its characteristic. An atomic mass unit defines one atomic mass unit as 1/12 of the mass of a single atom of the carbon-12 isotope. And it is commonly used to express the relative masses of atoms and molecules on a scale where the mass of carbon-12 atom is set to 12 atomic mass unit. And we discussed the difference between weight and mass also in our first topic, in general chemistry. And molecular weight, yes and no, it's the mass actually, but we use weight interchangeably. And this is the accepted common abbreviation, the MW, is the sum of the atomic masses of the elements present in a molecule's formula. And these two terms are also referred to as atomic gram and molecular gram. And also for the molecules, also sometimes we say the formula gram or the grams of formula, since the amount of substance is expressed in gram. So don't forget we expressed grams. So the 1 mole of carbon does, or the molecular weight of the carbon is 12 grams. Not, and so to understand the mole number, firstly we should understand mass. And then also example, look at the water, which the hydrogen as the mass number is 1 gram and oxygen 16. That's 1 times 2, which means 2 grams of hydrogen plus 16 grams of oxygen. So the water is 18 grams. Now it is time to understand the relationship between mass and the mole number, because we need to understand the mole number to prepare molar and equivalent concentrations. And it's essential. And the mole number, or 1 mole, was 6.02 times 10 to the power 23. And this is the famous Avogadro number defined by Amedeo Avogadro. Amedeo Avogadro was an Italian scientist. He lived between 1776 and 1856. And he is best known for his contributions to molecular theory and the development of Avogadro's law that we studied in the previous topic in matter and characteristics under title gases. Avogadro's law states that equal volumes of gases at the same temperature and pressure contain the same number of molecules. And this principle was a crucial step toward understanding the behavior of gases and laid the foundation for the concept of the mole in chemistry. Avogadro's work was instrumental in helping chemists reconcile the relationship between mass and volume in gases, ultimately leading to the determination of the Avogadro constant. And this constant now known as Avogadro's number. And this number represents the number of atoms, ions, and molecules in 1 mole of a substance. Avogadro's insights were not widely recognized during his lifetime, but his ideas became fundamental to the development of the atomic and molecular theories that underpin modern chemistry. And in his honor, the unit mole was named, which is used to express amounts of chemical substances, and it's based on the Avogadro's number. And 1 mole, I said, 6.02 times 10 to the power 23, which equals the atomic mass in grams. And also, if it's a molecule, molecular mass in grams. Such as here, the iron, its atomic mass is 56. So this means 1 mole of iron means 56 grams of iron. And 1 mole of aluminum means 27 grams of aluminum. And for example, what about oxygen? What about oxygen? So 1 mole of oxygen means 16 grams. If we want to weigh, for example, 5 moles, we will weigh 16 times 5, which the answer is 80 grams of oxygen. Yes, here is the famous periodic table of the elements and the recent version. And let's do some examples for about oxygen. So 1 mole of oxygen, we have to weigh 16 grams, and 3 moles, 48 grams. And another example, calcium. And if we get 5 moles of calcium and look at the mass of the calcium, 40, so 200 grams must be weighed to get 5 moles of calcium. And the carbon mass is 12. If you want to get 0.5 mole carbon, so we have to weigh 6 grams of carbon. So if you understand the mole number, the concept of the mole, it's time to pass to the molarity. Now it's time for molarity, the molar concentration, which we need to use the mole concept to calculate the molar concentration. The most common measure of concentration in the lab is molarity, and the definition is the number of moles of solid per liter of solution, and abbreviated as capital letter M or mole per liter, and which actually this is also the formula and the definition. So look at the definition. So molarity, the big M, equals the number of moles per liter of solution. So the mole per liter. So to prepare a molar solution, we need to get a volume of solvent by adding mass of element, and at the end we'll prepare a volume of solution. Don't forget, this is the volume of solution, not the volume of solvent. So if we weigh 1 mole of a molecule or a substance, and using this substance, this mass, prepare a 1 liter of solution, thus we will obtain a 1 molar concentration, or 1 mole per liter concentration. In preparing molar solution for solid chemicals and preparing molar solution from acids have different approaches. Because in the solid chemicals, this is the easiest one, you just weigh it and put in a volume and prepare the molar solution. But from acids, in nature, they are liquids, or we got the acid into our stock as a liquid chemicals. They are liquid chemicals. If we have a liquid chemical, this means it has already prepared in a molar concentration. Thus, first we have, in the first step, we will calculate the molarity of the stock chemical, because it's not given, we have to calculate, and then prepare the required concentration by diluting the stock solution, by diluting or dilution of the stock solution. And this is the formula that can be used. But I don't prefer to use the formula. Instead, I will use the basic steps of calculation. So let's do an example about the solid chemicals. Think about, before doing it, let me to delete these areas to open an empty place. Yes. Oh, not this one. Okay, the sodium hydroxide. So according to the definition, to prepare a 1 molar concentration of sodium hydroxide, I have to weigh 1 mole of sodium hydroxide and prepare in 1 liter of solution. But don't forget, this is not the solvent. This is the volume of solution. So to do it, when I weigh 1 mole of sodium hydroxide, then I will take a volumetric flask having the capacity of 1 liter. Then I will put the weighted sodium hydroxide crystals into the flask and then fill up the 1 liter. And finally, I will get the 1 molar concentration of sodium hydroxide. So, but how we calculate the 1 mole of sodium hydroxide? And the answer is very easy. According to the definition of mole, 1 mole of a substance equals to its molecular weight. And the molecular weight of the sodium hydroxide is 40 grams per mole. So if I weigh 40 grams and prepare 1 liter solution, so I will obtain 1 molar concentration of solution. That's a molarity. And the second one, third one, sorry, not the second, because the first one is percentage, second one molarity, and this is the third one, equivalent concentration, or the normality. The equivalent concentration or normality of a solution is defined as the molar concentration divided by an equivalence factor. Equivalence factor. In another expression, solutions containing 1 equivalent gram substances per liter are referred to normal concentration as seen here. An abbreviation is the big or the capital letter N, and equivalence per liter, or sometimes valance per liter. Now we have a same feature here to prepare equivalent concentration from certain chemicals and to prepare equivalent concentration solutions from acids require different approaches, and the approaches are same with the molarity. In solid, just wait, but in acids, as in the molar concentration, we have a two-step approach. In the first step, calculate the normality of the given stock solution, then dilute it to prepare the required concentration in your experiment. Also, we have the formula and the difference. If we compare the formula of normality and the molarity, the difference is in the denominator side, which in normal we have an equivalence factor. And the equivalence factor is determined by the features of the chemical, whether it's an acid, base, salt, or its redox state. In Bronsted-Levy acid and bases, we look the number of hydrogens in an acid, and in base, number of hydroxyl groups. If it has, and let's do an example. Look at the hydrochloric acid compared with the sulfuric acid. And to get the valance, we have to divide by according to concentration, according to definition. So the molecular weight divided by the equivalence factor, which is the number of hydrogen. So in hydrochloric acid, it is 1. This also means the normality and the molarity of the acids or bases having 1 hydrogen or hydroxyl group are same. What about the sulfuric acid? Look at here, there are 2 hydrogen, which makes the equivalence factor 2. So to prepare a normal concentration, normality or the equivalence concentration using the sulfuric acid, we have to weigh the molecular weight divided by 2. And the molecular weight of the sulfuric acid is 98. To prepare 1 molar concentration, we will weigh 98. But to prepare 1 normal concentration, we have to weigh 98 divided by 2, which is 49 grams. Thus, we have an equation like this. Normality equals the molarity times the equivalence factor. Actually, here in the definition, you should read the molar concentration divided by an equivalence factor. Actually, this means the molecular weight. It's mole number. I mean the mole number. And a clear slide showing the differences between molarity and normality. So the denominators are same, the volume of the solution, but the numerator is different. In molarity, the moles of solute. In normality, valance or equivalence of the solute or the equivalence gram of solute. When a solution contains a very small concentration of solute, concentration is often expressed in parts per million ppm or parts per billion ppb. And also there are even smaller units, such as ppt, parts per trillion, and ppq, parts per quadrillion. And collectively, for all of them, we call part per notation, which signifies the quantity of a specific component present in a solution or mixture. And the parts may be expressed in either mass or volume units as long as the same unit is used for both the numerator and denominator. And here's an example: 1 milligram per kilogram or 1 microgram to gram equals 1 ppm. 1 microgram per kilogram, 1 nanogram per gram equals 1 ppb. Yes, here you see the SI units, the units of prefixes, submultiplies, multiplies, and the symbols. And these prefixes and multiplies help express SI units at different scales, and this is the scale. And it makes you to understand better how we convert from one level to another level, or from one scale to another scale. And especially we study at the level of milli in general to the smaller or to the lesser degrees. From the milli to micro, nano, pico, femto, atto, zepto, nyacto. Look at the level of degrees from -3 to -24, and even there are more after gyokto, such as ronto and kuekto. So mind-blowing levels, very small levels. As I briefly explained the dilution in previous slides, dilution is the addition of solvent to decrease the concentration of solute. And sometimes we have solutions in a higher concentrations than the required. And in this case, we do dilution to lower the concentration to the concentration we required. And so in the initial solution to the diluted solution, we add dilute with more solvent. So the diluted solution contains the same number of molecules, but in a large volume. In scientific terms, dilution is often expressed in terms of ratios of concentrations. For instance, a dilution ratio of, for example, 1 to 10 or 1,10 means that 1 part of the original solution is mixed with the 9 parts of solvent, resulting in a 10-fold dilution. And we do it in the lab. And we finish the first major title. The second major title of this topic is Biophysical Phenomena, and we will discuss osmosis and osmotic pressure. The following are dialysis, diffusion, surface tension, and adsorption. Osmosis and osmotic pressure. The membrane that surrounds living cells is an example of a semi-permeable membrane. A membrane that allows water and small molecules to pass across, but ions and large molecules cannot. Osmosis is the passage of water and small molecules across a semi-permeable membrane, from a solution of low solid concentration to a solution of higher solid concentration. In short, the addition of water to the solution by passing through a semi-permeable membrane is called osmosis. Osmotic pressure is the pressure that prevents the flow of additional solvent into a solution on one side of a semi-permeable membrane. In other words, it is the pressure caused by water or a solvent osmosing a low-density dissolved substance into a high-density dissolved substance. And the osmotic value that works itself during osmosis event is called the osmotic pressure. In other words, it is the suction force resulting from the cytoplasmic density of the cell in a living being. And osmotic pressure depends only on the number of particles in a solution. The greater the number of dissolved particles, the greater the osmotic pressure. An example, a 0.1 molar concentration sodium chloride solution has twice the osmotic pressure as a 0.1 molar concentration glucose solution, since each sodium chloride is composed of two particles, sodium cation and chlorine ions. But in glucose, only one particle dissolved in a molecular state. So, the osmotically active numbers of sodium chloride is greater than the osmotically active number of glucose solution. Thus, provide more osmotic pressure. And this figure showing or explaining osmotic pressure by using a U tube. In the A, which is the initial state, the dilute solution of glucose in water is placed at the right arm of the U tube, and the left arm is filled with pure water and is associated to the same height. And there is a semi-permeable membrane separates the two arms. Since the flow of pure solvent from this membrane from left to right, which means pure water to the glucose solution, is greater than the flow of solvent in the opposite direction, and the liquid level in the right tube rises, as in the B tube or the B figure, which is the equilibrium state. It's depicting the equilibrium state. At equilibrium, the pressure difference equal to this difference equal to the osmotic pressure of the solution. And this pressure equalizes the solvent flow rate in both directions. And the C here, which the external pressure applied. So the applying an external pressure equal to the osmotic pressure of the original glucose solution to the liquid in the right arm reverses the solvent flow and restores the original state. So, as you see in the osmotic pressure or in the osmosis, the water flow from a lower solid concentration to the higher solid concentration area. In other words, water flow from a high water potential to the low water potential area. Since cell membranes are semi-permeable and biological fluids contain dissolved ions and molecules, and osmosis is an ongoing phenomenon in living cells. Fluids on both sides of a cell membrane must have the same osmotic pressure to avoid pressure buildup inside or outside the cell. Any intravenous solution given to a patient, therefore, must have the same osmotic pressure as the fluids in the body. But it depends on the situations. It depends on the situation. And here, this statement is about the normal physiology is about the conditions that the osmotic pressure is in balance. Because due to the imbalance in osmotic pressure, we may apply or the physicians or the vets may administrate solutions having different characteristic or different osmotic pressure, and so this is under control of the physicians or the wet surgeons. Few solutions with the same osmotic pressure are said to be isotonic. Isotonic solutions used in hospitals include 0.9% sodium chloride solution or 0.5 correction 0.15 or 0.15 molar concentration of sodium chloride solution and 5.0% glucose solution. All of these solutions do not contain exactly the same ions or molecules present in the body fluids. They exert the same osmotic pressure. And this is so critical. And also this is a common question, such as which of the following solutions has the isotonic pressure or has the isotonicity comparing the blood plasma? And the answer will be isotonic 0.9 or sodium chloride solution. It is also called saline, shortly saline, or physiological salt solution, physiological salt solution. What happens if a red blood cell is placed in a solution having a different osmotic pressure? A hypotonic solution has a lower osmotic pressure than body fluids. And the hypotonic solution has a higher osmotic pressure than body fluids. And also we have an isotonic solution, has an equal osmotic pressure compared to the body, or equal to the body fluids. And let's discuss if we administrate hypotonic solution to the body or hypertonic solution. And don't forget, I mean a normal physiology or in a healthy state. In a healthy state, if a hypotonic solution is administered, the concentration of particles outside the cell is lower than the concentration of particles inside the cell. In other words, the concentration of water outside the cell is higher than the concentration of water inside the cell, so water diffuses inside. And as a result, the cell swells and eventually bursts. And this swelling and rupture of red blood cells is called hemolysis. In a hypertonic solution, the concentration of particles outside the cell is higher than the concentration of particles inside the cell. In other words, the concentration of water inside the cell is higher than the concentration of water outside the cell. So water diffuses out of the cell. And as a result, the cell shrinks. And this process is called crenation. And also, sometimes it is called notching. But we prefer crenation. The osmotic pressure of intracellular and extracellular fluids in humans and animals is equivalent to the osmotic pressure of 0.9% sodium chloride solution. And here, as you see, the isotonic state, which the flow of water from outside to inside or inside to outside occurs in normal manner. And cells and blood cells continue their normal functioning in neutral environments close to the osmotic pressure, which I mean the isotonic pressure. And serums and intravenous injections given to the patient should always be solutions with this osmotic pressure. But don't forget, there are exceptions. And here in this part, hypertonic part, as you see, this means if the tonicity of the extracellular fluid is higher than the hypertonic conditions, the cells lose its content, its water content, and shrinks, so crenation occurs. In an hypertonic solution, cells swells and lysis occurs. And the lysis of the red blood cells is called hemolysis. And here you see a good figure showing the changes in erythrocytes in red blood cells when put in a dilute saline solution, as you see, which is isotonic, 0.9% of sodium chloride. There's no change, and the erythrocytes preserve their donut-like shapes. But if you put them into a distilled water, an example of hypertonic solution, look at the shapes. They swell and the lysis will occur eventually. And when we put them into a dense saline solution, such as 5% sodium chloride, the cell loses their shape, shrinks, and we call it the crenation, as you see. Dialysis. Dialysis is a process that involves the selective passage of substances across a semipermeable membrane, and the membrane is called the dialysing membrane. And you see in the figure at the start of dialysis, which there is a dialysing membrane put in a solvent, and there are particles. They differ in size, smaller particles and the larger particles. And also inside the dialysis membrane, it represents a concentrated solution. And after a while, these smaller molecules can pass through the cell membrane to join into the solvent, and the bigger molecules cannot do it. So this means in dialysis, water, small molecules, ions can travel across the membrane. Large biological molecules like proteins cannot. And thus this is a process of filtration. This is a process of filtration according to the size of the molecules. In other words, it's a kind of separation of larger molecules and smaller molecules. In the mammalian body, blood is filtered through the kidneys by the process of dialysis. Each kidney contains over 1 million nephrons, tube-like structures with filtration membranes. And these membranes filter smaller molecules, glucose, amino acids, urea, ions, and water from the blood. And the ones which will be recycled, are then reabsorbed, but urea and other waste products are eliminated in urine. Diffusion. Diffusion is the net movement of molecules or atoms from a region of high concentration or high chemical potential to a region of low concentration or low chemical potential. This is also referred to as the movement of a substance down a concentration gradient. In this case, as the particles become smaller and the temperature increases, the diffusion speed increases. And there is no membrane between the two phases. And here you say the phases, but there is no membrane. There is a region of high concentration and the low concentration. And so diffusion is the net movement of substances from a high concentration to low concentration area. What is the biological significance of diffusion? Diffusion plays key roles in the matter exchange of organisms, such as oxygen. Oxygen flows from the air to the blood and then to the tissues by the diffusion. And passage of foodstuffs into the bloodstream occurs via diffusion, and also spreading of drugs where they are injected. And the photograph of occurring events at certain phases dye a concentrated matter into a liquid, into water, and then spontaneously from a higher concentration to the lower concentration area, the particles move till the equilibrium state. And yes, here you see two famous photos here, which is explained by the surface tension. The cohesive forces between liquid molecules are responsible for the phenomenon known as the surface tension. And also we discussed this phenomena in the previous topic, in the matter topic in the liquids titled the cohesion, adhesion, and surface tension. The molecules at the surface do not have other like molecules on all sides of them, and consequently they cohere more strongly to those that are associated with them on the surface. And this forms a surface film, which makes it more difficult to move an object through the surface than to move it when it's completely submerged. Without surface tension, even the smallest objects would sink underwater. Large particles of dust would not float on the water, but instead the particles would sink to the bottom and kill all of the marine life, causing the collapse of ecosystems. Water particles at the atomic level help keep the cell membrane from collapsing on itself. Water is a critical component in cytoplasm, the jelly-like substance that fills the cell. This means that the surface tension of water allows the cytoplasm to hold up the cell membrane. If the pressure is too extreme, then the water breaks down the cell membrane and the cell drowns. What is the significance of surface tension? And let me explain the significance of surface tension by giving some examples. A razor blade or pin does not sink when gently dropped on the surface of the water. Small insects can walk on the surface of the water without sinking. These phenomena and also the phenomena such as water rising in fingerglass tubes and filter paper and gas rising in a lampwick are phenomena associated with surface tension. And there are substances that increase surface tension and substances that decrease surface tension. And the most important one for me is the bile. We need bile to digest fats and oils because bile decreases surface tension of biles, surface tension of lipids, which are contained in the diet. And the last one is absorption. Absorption is a process in which atoms, molecules, or ions from a gas, liquid, or dissolved solid adhere to a surface. It occurs when there is an attraction between the particles in the substance and the surface they come into contact with. This process is different from absorption. So be careful. This is absorption. This is adsorption, where a substance is taken up into the bulk of another substance. Absorption is directly proportional to the surface area and the quantity of the absorbing substance and inversely proportional to the ambient temperature. Substances that exhibit distinct qualities in retaining other substances on their surfaces are referred to as absorbents. And absorption plays a crucial role in various fields, including chemistry, physics, material science, and biology. It is widely used in applications such as catalysis, gas purification, water treatment, and chromatography, and drug delivery systems. Absorption-based methods are extensively utilized for the separation and purification of specific substances from mixtures. Absorption methods find significant application in biochemistry. Large molecules and colored substances are absorbed by materials such as animal cocoa and other absorbents, enabling their differentiation and purification from solutions. The color of urine, for instance, can be eliminated by shaking with animal cocoa and effective absorbent material. Hormones and enzymes are absorbed by aluminum oxide at specific pH levels and can be separated from each other when there is a change in pH. And my dear friends, this is the end of this topic. And the references I suggest you for further reading. Next topic, acids and bases. And for more about biochemistry, clinical biochemistry, and the laboratory world, visit biochemia.vet. And you can also follow my Instagram account, biochemia.vet. Don't forget to subscribe, click on thumbs up, and open notifications for further news. See you in our next topic. Goodbye and stay safe.